Okay, Calc, we're moving on into chapter 7, which is exponential functions. Here at the end of this chapter, we're going to start doing derivatives with exponential functions. So, but we got to kind of talk about and do some background of exponential functions. So this is going to feel like a lot of review. So algebraic functions is what we've been dealing with so far, which are polynomial functions. So like x squared or x to the fifth power. And then also we have like some rational functions, which would be like 1 over x squared. Things like that. The square root of x. Those are all going to be algebraic functions. But now we're getting into something called transcendental functions, which are going to be your exponential and log functions. Okay, so those are lumped into that category. I don't know that we've ever had that vocabulary word before, transcendental, but that's what exponential functions and log functions are kind of lumped into. Okay, so an exponential function is going to be some number to an exponent. Okay, where this exponent has to be, my variable. So my variable is now in the variable. My variable is now in the exponent rather than being as the base. So exponential functions are not things like x squared. Okay, not x squared. But if I flip that around and make that 2 to the x power, that's an exponential function. Okay, because my variable is now in the exponent. Okay, so examples of these would be 4 to the third power equals 64. 4 to the 1/2 power. So this is an example of like 4 to the x, and we would be plugging in the numbers 3 and the numbers 1/2. Okay, so that's an example of an exponential function. Now remember that anytime you have a fractional exponent, that's just going to be a root. So 4 to the 1/2 power would be like the square root of 4, which of course is 2. 4 to the 1/3 power is going to be the cubic root of 4, etc. Right? Okay, so just keep that in mind. We did that a lot with derivatives and stuff. Graphs of exponential functions. These two up here at the top are going to be growth functions because they are growing over time. And a standard, kind of principle of exponential functions that are growths, they're all going to hit at the point 0, 1. Okay. No matter what it is, if it's 4 to the x power or 2 to the x power, it will always hit at 0, 1, because if I would plug 0 in for x, 4 to the 0 power is going to be 1. 2 to the 0 power is going to be 1. So that's why he's touching at those places. In addition to that, they will all have a horizontal asymptote here at y equals 0. Okay, each one of them will level out at y equals 0. Okay, that's what those exponential functions will look like. And then they will grow. They will become steeper the larger the number is. So this is going to be steep, steeper than the 2 to the x power. Okay, it's kind of like a linear function. The larger the number, the steeper it's going to be. So this 4 to the x power is this guy right here. This is your 4 to the x power. Okay, the 2 to the x is this one, which is a little bit more shallow. It's not going up quite as quickly as what the 4 to the x power is. Okay, so that's what those growth functions will look like. Now you know that it will be a growth if your exponential function is a to the x power. If this number is a number that's greater than 1, it's going to be a growth. Okay, now I have a lot of people say that it's a decay, which is what these guys are. Decay if a to the x power, if this a is a fraction. Okay, which is not quite true. A lot of people think of fractions as like 1/2 or 1/3, in which case it would be a decay. But I could also have this a up here be like 3/2, which is actually bigger than 1, and that's going to be a growth function. So be careful, it's not just fractions, it's numbers that are specifically bigger than 1 and numbers that are specifically less than 1. Like 1/2 or 1/3 or things like that. That's going to be a decay function where it's going to start up here and it's going to decrease over time. Okay, it's still going to have those horizontal asymptotes at y equals 0. Okay, still going to touch at 1 here. Okay, but it's just going to be decreasing instead of increasing. Okay, and a lot of times they will note that as 4 to like the negative x power. Okay, because this negative inside of the exponent is a reflection over the y-axis. Okay, So it's basically taking this function that was here before, and that negative inside the exponent, this negative right here, will flip him the other direction. So they'll sometimes write your decay function like that instead, okay? So if they say 3 to the negative x power, okay, 3 to the negative x power, that would be the same thing. If you're trying to make a negative exponent positive, you flip this number down to the bottom, and that would be the same thing as 1/3 to the positive x power. That's what he would look like, okay? So sometimes they might write it and they might disguise it as this is a number bigger than 1, but if they put that negative in there, you just kind of have to think about it being the reciprocal of that, and then it is in fact a number that is less than 1, okay? So kind of be careful of that. All right, going on the back side. We've dealt with all these before, and if you have your transformation sheet and don't have these memorized, they're all on there, but this is kind of the same thing as what all of the algebraic functions are. If you're adding a number onto the end, you're just moving them up or down. If you're adding and subtracting a number within the x, it's a horizontal translation. Multiplying numbers, adding negatives is going to be a reflection, that type of thing, okay? So if you need to use this chart or the chart that you have, go for it. They're saying that we're going to start with 3 to the x power, and then they just say describe the transformation, okay? So if I start with 3 to the x power, basically they're saying, what is that 1 doing, okay? And I have a lot of people that might think that that 1 is moving him up 1, but up 1 would actually look like this, where the 1 is off to the side. That would be up 1 unit, okay? This, if you want to insert parentheses in there, that's kind of like the adding 1 inside of parentheses. And when you're inside parentheses, you always do the opposite of what you think it would be. So +1, I would think that it would be to the right 1. This is actually moving him to the left 1 unit, okay? So my exponential function that is increasing like this would now be to the left 1. So this guy is going to be over here and doing one of those, okay? So that's what he would look like instead, left 1, all right? This guy is, we're asking what the -2 is doing. That's moving him down 2, okay? That's what he's doing. So I'm taking this function and I'm moving him. Basically, his horizontal asymptote would be down here now at -2, and he's going to go like this, okay? And then this one, the negative inside of the x, okay, there's a difference between 3 to the negative x power and -3 to the x power. This guy, when the negative is in front, if you look at the kind of the reflection here, when there's a negative in front, this is going to be over the x-axis, okay? So that, if I have my exponential function here, over the x-axis, is going to move him down here like this. That's what this one would do, okay? But 3 to the negative x power is actually going to, kind of like what we talked about on the front side, this is going to go over the y-axis, okay? So he will actually do this, and he'll level off. Oh, I cannot draw my, whatever, make that look a little bit better than mine. But anyway, so that's what he would look like. He would be over the y-axis, so you're reflecting him that way, okay? Another way of thinking about that, 3 to the negative x power is like what I said, 1/3 to the positive x power, and that's going to be your decay function like that, okay? I don't get really picky on your terminology, so you can say a reflection across the x-axis, or you can just say over y. I know what you're, or over x, you know, I'll know what you mean. You can say a vertical translation down 2 units, or you're going to say down 2, or an arrow with a 2, okay? I don't know why I missed a T there, but left 1 would be a horizontal translation to the left 1 unit, or you're going to say left 1. I'm not real picky on that, okay? All right, I'm going to go down to this bottom right here and do an example for compound interest, and then I'll kind of talk about what E means, okay? So when you are compounding interest, when you're doing compound interest, like a bank does, except a computer does it for them, compounding interest, the compound interest formula is this guy, okay, where P is going to be your principal, your interest rate is going to be R, that's this guy right here. So that's like you're earning an interest rate of 3%, even though in a bank you probably would earn like maybe 0.3% if you're lucky, okay? N is going to be the number of times it's compounded. So the number of compounds per year, okay? And the number of compounds per year just says how many times is your interest calculated per year, okay? And then T is the time that you want to evaluate your money. So the time that you want to take your money out. So I'll put time that your money is taken out. Or maybe you're not even taking it out. Maybe you're just looking at how much money is in there. So the time that has elapsed, okay? So that's what all those variables are going to mean, okay? So I went ahead and did an example down here. We're going to put $500 in at 3% interest. So it's earning 3% interest. And we're going to do that quarterly, okay? And then I want to know how much it's going to be after 10 years. So this is going to be my T. Quarterly is going to be my N. And if I'm doing it quarterly, that means 4 times per year. 3% is going to be my R. But be careful because R isn't going to just be 3. It's going to be 0.03, okay? Because we have to convert that to a decimal. And then P is going to be what 500 is, okay? So let's figure out how much this is going to be worth after 10 years. A is going to be like the after amount, okay? And I'm just plugging these numbers in. So 500, 1 plus that 0.03 has to be divided into 4 equal pieces because I'm compounding it 4 times per year. Okay, and then I'm doing 4 times T, which is my N. Okay, or 4 times 10, which is my T. Okay, so I'm going to type this all in. You should be able to do this all at one shot, I think. 500 times 1 plus 0.03 divided by 4, close parentheses, to the, I'm just going to put 40th power. I'll do that in my head. Okay, and he ends up becoming $674.17. Okay, which is, I mean, not a whole lot, but it's $174 interest that I would have not made in the first place. It's basically like free money just by it sitting there. So that was compounding quarterly. If I would compound it more frequently than that, so compound it monthly, meaning 12 times per year, it would end up probably making me just ever so slightly more than $674, maybe $680. The more times you compound per year, the more money it's going to make you. So what they've done is they've figured out that if I compound it monthly versus quarterly, or daily versus monthly, or hourly versus daily, that this part right in here, the 1 plus R over N, the more times you do it, so maybe I'm doing it an infinite number of times in a year, like per second or per millisecond, this part right here actually ends up approaching the value of E, which is 2.7182818, blah, 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 that big long decimal number. And that is kind of like pi in your calculator. I have an E button, which is right here. It's right next to the LN, so I have to hit shift in order to hit E. Okay, but the more times you do it, the more this part of your formula, really, it includes the N as well, this part of your formula approaches that value of E. So they basically get rid of this part of the formula to do compound interest or continuous compounding interest, and they replace it with E, which is the PERT equation, okay? So now I'm going to do the same information, but rather than quarterly, I'm going to do compounding continuously, which means like every blink of an eye, I'm compounding my interest, okay, and figuring out what that would be. So, so for PERT, A equals, P is going to be 500, E to the interest rate is 0.03 times T is 10, okay? And this is a much easier, nicer equation that I have. I like dealing with PERTs, so 500, I'm going to do second E, and I have 0.03 times 10, close parentheses. Okay, and that's going to end up making me, oh, really, not a whole lot more than that, $674.93. Whoop-de-doo. So it's really not a whole lot of a change between quarterly and compounding interest, but it's 80, maybe 76 cents more, okay? So difference between compounding interest and continuous compounding interest. That part in the middle will become E the more times you compound it. So as that X approaches a larger and larger and larger number, so it goes from 4 to 12 to 365 to every minute to every second, that approaches a value of E, okay? Because it gets to the point where the more times you compound it, it's just going to cap out at some point which is that number of e, okay? So there you go. That's what I have for this section. We're going to get more into logs and exponential functions, and then we'll start doing derivatives with them, okay?